So let's look at some examples of how we would use the ratio test to determine convergence. This one, for example, we've got 3 to the n over n factorial, and notice here the a sub n is the 3 to the n over n factorial, and what we want to do is find a sub n plus 1. Well, that just means I replace the n's with n plus 1. So we've got n plus 1 factorial here. And what the ratio test calls for is the evaluation of this limit. It asks for us to evaluate that limit. Now, so let's do that. Here we go. We've got the limit as n goes to infinity. Now I'm going to just drop the absolute values because there's no reason to have it here. In other words, I'm just going to look at this as 3 to the n plus 1 over n plus 1 factorial. This is always going to be positive. And I'm dividing that by 3 to the n over n factorial. In other words, I've got n factorial over 3 to the n. See? And I'll just do it like this. There's no need to have the absolute value in there. Okay, now what I want to do is simplify this, and I want to figure out what this limit is. Now remember, if this limit is less than 1, my series converges. If it's bigger than 1, it diverges, and if it's equal to 0, the ratio test doesn't even apply. But let's see how we would evaluate this. We need to simplify the factorials in there and that exponential term. So let's see what we've got now. We've got the 3 to the n plus 1 over the 3 to the n. Now, notice that's just going to be, and let me do a top and the bottom here. That's just going to be a 3 on top. So now we've got 3n factorial over n plus 1 factorial. I'm just doing this a step at a time. In other words, if I divide this by this, I subtract the n and I'm just left with 3. 3 to the first. We subtract off the n. So 3 to the n plus 1 minus n is just 3. That's how I got that. I just subtracted the exponents. Now I got to deal with these factorials. So let's see what I've got here. I've got the limit as n goes to infinity of 3 times n factorial over, let's do this. Let's do n plus 1 times n factorial. And just do that little trick where n plus 1 factorial is the same as n plus 1 times n factorial. And the reason I did that is because, dig this, those cancel. And now let's see what we have. We've got this situation, the limit as n goes to infinity of 3 over n plus 1. Well, this is an easy limit. That's just 0. And 0 happens to be less than 1. Therefore, by the ratio test, that series converges. So by the ratio test, I guess we could call it RAT, right? Ratio test. Okay. So by the ratio test, that series converges. Okay, now let's look at another one. Okay, let's suppose that we've got, let's say n equals 1 to infinity, and we'll go with 5 to the n over n to the fourth. Suppose we've got that one. And I want to determine whether or not this one converges. So here I go. I need to find, I know what a sub n is. Let's find a sub n plus 1. Well, that's going to be 5 to the n plus 1 over n plus 1 to the fourth. So now let's look at the ratio test. We've got the limit as n goes to infinity of, let's see here, 5 to the n plus 1 over n plus 1 to the fourth times multiplied by the reciprocal n to the fourth over 5 to the n. Okay. Well, let's see what we have then. As far as the fives go, Dig this. We have 5 to the n plus 1 over 5 to the n. Well, that's just 5. So let's see what we have. We have the limit as n goes to infinity of 5 times n to the fourth over n plus 1 to the fourth. Now, that 5 really doesn't have anything to do with the limit. In other words, it doesn't really have anything to do with what n does. I mean, it's part of the limit, but really, if you look at this, up top we've got n to the fourth, and on the bottom we've got n to the fourth. If you expand out the bottom, which you don't need to, you would notice that your leading term was just a 1 n to the fourth. And up top we've got an n to the fourth. So whenever you have the degree on the top and the degree on the bottom are the same, remember it's the ratio of the leading coefficients. So we've got 5 n to the fourth over 1 n to the fourth. That's just going to be 5 over 1. So this limit is 5. Well, that's bigger than 1. So we have that the series diverges. Okay, let's look at one more here. Let's suppose we'll make it look a little more complicated. Now, some of these can be challenging. Sometimes it's a little bit challenging to simplify the limit at the end and evaluate the limit, but we're just trying to, those just require practice. We're just trying to get the idea here. So we've got n factorial over n 3 to the n. Let's try this one. And I haven't been putting in the absolute values because none of these have required it because they've all been just positive terms. If we had an alternating sequence, an alternating series, then I would go ahead and put in an absolute value. But let's see what we've got here. We've got the limit as n goes to infinity. Now, here's what I want to do. I want to, first of all, plug in. Now, look, I'm thinking I'm going to need to cancel out this n factorial in a minute. So instead of writing n factorial, let me just do this. So this is a shortcut. I'm going to write this as n plus 1 times n factorial. I'm writing n plus 1 factorial this way. And now down here, I've got n plus 1 times 3 n plus 1. Okay, so right there, that's a to the n plus 1. Note, really, the only thing different I did was I just went ahead and wrote n factorial as n plus 1 times n factorial. Now, let me divide by a sub n. So I've got n 3 to the n over n factorial. I'll multiply by the reciprocal. Now you can see why I went ahead and did this. These factorials get rid of each other. And it looks like this is going to get rid of each other too. Okay, so now let's see what we've got here. We've got the limit as n goes to infinity of, let's just take a look here. Up top, we've got n, and on the bottom, we've got 3. Yeah, there we go. Well, that's infinity. Okay, that goes to infinity, which is bigger than 1. So this thing diverges. Diverges.